I'm so sorry. This was supposed to be taken care of before the presentation. 1 second. Yeah, it's me. I told you I didn't want the DeLorean. It's overused. I know it's iconic. Look, this is the second time travel debugger I've built in my entire career. You'll never guess what pop culture iconography we used the last time. Yes, the DeLorean. Please, anything else? Okay, show me what you got. Oh, okay, that's not bad, right? That's H.G. Wells, right? The OG, the time machine. I like it with the elephant. Not exactly contemporary, but, you know, that's an improvement. What else? No, I don't think the Terminator is the vibe we're going for this week. Can we perhaps come up with something else? Okay, yes. Bill and Ted, this is perfect. Thank you so much. I actually have a great story about this. My wife's friend and her kids came to stay with us a few years ago, and they'd never seen Bill and Ted, so we showed them Bill and Ted. And the very first time the time-traveling phone booth arrives on the screen, I lean over to them and say, do you guys know what that is? Because this is the 21st century. They're kids. What would they know about a phone booth? The oldest daughter looks at me and says, of course I know what that is. That's a TARDIS. Slow clap for the mom, man. Okay. We're not here, though, to talk about pop culture time travel. We're here to talk about Postgres time travel. So I'd like to start with a show of hands. How many people here have ever used the native built-in support for time travel queries in Postgres? No hands. How many people here were even aware that Postgres had native built-in time travel query support? 1, 2, not many. Well, so that's kind of interesting, right? It was actually a feature of Postgres from the very beginning. There's this great white paper that came out a couple of years ago about the history of the Postgres project. And if you read through the section about the storage engine, it talks about how Stonebreaker was trying to get away from write-ahead logs. He had this theory of data is log, log is data. And in that section, there's this great quote. This design also enables time travel queries. You can run queries as of some wall clock time and access the versions of the data that were committed at that time. Now, this is a really powerful tech. How come nobody in this room has even heard of it? Because it was removed from the product about 25 years ago. I grabbed this screenshot off the Postgres website last week. 6.3 is the oldest version of Postgres documented on that website. Obviously, there were more versions before that. And you'll see here that there is actually a higher page for time travel under advanced Postgres SQL queries. First line of it says it's no longer supported as of 6.2. And in case you missed that sentence, there's this other drop-down box that says, hey, this has really been deprecated. And you'll notice the timestamp on this note is January 1998. So if you really wanted to use the native built-in support for Postgres, you would either A, need a time machine, or B, be willing to run a 25-year-old unsupported version of Postgres in production. Neither of those seem particularly realistic or, reasonable today. Which is kind of too bad, right? Because this is great technology, right? Now, I personally am a developer tools engineer. That's what I do. That line at the beginning about having built 2 time travel debuggers in my career, that's straight up fact. So as you can imagine, I have a favorite on this list, the debugging. But I imagine that there are a lot of folks at your companies who care about things like auditing and regulatory compliance. Stonebreaker talks about recovery in the context of the work that we do at DBOS, which is the company that I work for. It's Stonebreaker's most recent startup. And periodic reporting, which sort of falls into auditing and regulatory compliance. Now, the Postgres community being what it is, and since you're part of the Postgres community, it's not exactly a community that'd be willing to let good ideas die on the vine. So over the intervening decades, we've seen a variety of other implementations of this kind of technology become available for Postgres. Lots of different implementations. But these implementations all work basically the same way, right? For every app table you have a history table or an audit table. And for every change that you make to your app table, you'll have an extension or a trigger or some other mechanism that will replicate the information about that change from the app table into the audit table. Unfortunately, this has some pretty significant downsides, right? First off, it's a significant performance hit. You see write amplification because every write to your app table is turning into at least one additional write to the history table. It also creates significant bloat in the size of your database. It's kind of like running Postgres without the vacuum. That's actually one of the reasons why the feature was removed from Postgres natively in the first place. If you go back to that page we saw a minute ago, it talks about data bloat being one of the primary reasons why it's removed. And of course, we all know the bigger your database, the slower it gets. It turns out that it's also extremely difficult to maintain. There was a talk yesterday by a gentleman from the Seattle Postgres user group talking about, he did it at the Postgres user group a month ago, so I got to see it early. And he's talking about how hard it is to handle schema updates in Postgres. And that's for any database, right? That's not a Postgres problem, that's a production database problem. Well, this approach doubles the number of tables. And you have all this connective glue that you have to maintain in order to replicate the changes from one to the other. So this turns your upgrade process into a nightmare, or a bigger nightmare. I'm a developer, not a DBA, so I don't have to normally deal with that kind of stuff. So at DBOS, we've taken a different approach for supporting time travel. This is a huge deal to us. As I mentioned, Michael Stonebreaker is our CTO, one of our co-founders, so this is a feature that he has believed in for decades. So when we approached this for DBOS, we took a different approach. First off, we put the stuff in a different database. This is not rocket surgery, right? We've been pulling data out of production transaction systems and putting them in separate analysis systems for decades, right? So this is relatively obvious in retrospect. It solves the vast majority of your performance problems, right? Sure, you've got write amplification on a different machine. Sure, you have data bloat on a separate machine. And your usage characteristics of your analysis service, of what we at DBOS call the providence database, those usage characteristics are radically different from your production database. Now, we pull the data out using logical replication. So this is not to say that there is zero impact on the AppDB. There is a small impact. The same as what you get if you're doing log shipping or logical replication in order to have a hot backup standby server. It's the same exact impact, right? And it also means that it's built in, right? This is infrastructure that is supported on every implementation of Postgres that's out there, including all of the big cloud providers. You don't need to install some kind of custom cool extension or anything like that. This is just built-in support in Postgres. Now, of course, if we just took that logical replication, we wouldn't end up with a time travel database, we'd end up with a replica. So we transform that into something we refer to as the multi-version format. And we'll talk about the details of this. But essentially what we're doing is we're keeping track of every single version of every single row in your database. So we keep the complete history, including the information about the transactions where those changes occurred. Now that's great. The problem is that it's hard to work with. So we also provide what we call the time travel proxy. So this is an executable that sits in front of the Providence database that makes the Providence database look and act like your application database, except that you can also do time travel commands to set the current idea of now as you see fit. Now we're going to talk about all this stuff on this slide for the rest of the talk. And I should have had a clock handy just to make sure. Okay, so let's first start with the multi-version format. We are tracking every single change and associating it with the transaction ID that caused that change. Every single table in the Providence database is a shadow of for the application tables, for your data, right? We don't do this for system tables, and for DBOS, we have a bunch of our system tables that we track that we don't do this with. But for your application data, we do we have for every column, for every table in your database, in the Providence database, we have a shadow that has these extra columns, begin transaction and end transaction. So this specifies what transaction created the row and what transaction deleted the row, if any. Right? Because if this is the current value, we're not going to actually have an end transaction ID. We use a, I think it's max int as a sentinel value for end transaction ID. And updates are modeled as essentially an insert and a delete followed by an insert. So there's no special handling for updating. Each version of the row is visible for a transaction ID between these two values. Who here knows anything about the internals of Postgres? Anybody? A couple of people. And you might say, that sounds kind of familiar, because this is essentially what Postgres does under the hood. If you, in your application table, there are a begin and end transaction column. You can't see them, you don't get to manage them, but that's what Postgres uses in order to manage the visibility of your changes on a per transaction basis. And we'll talk a little bit more about this later, but it's essentially the same idea. We're just leaning into it and taking that information that is implicit and invisible in your app database and making it explicit and visible and usable in your history database. So let's see an example of what this might look like. This is from the incredibly graphically well-designed widget store application. It's one of the DBOS sample applications. And DBOS as a company is primarily focused today on building a durable execution framework. And so we have this sample e-commerce website, and there's a long-running process that lives behind the green buy button, and you can crash it. In fact, we actually have in the full version of this, like a crash, you'll see it later, crash button, so you can terminate the app and it'll automatically restart. We're not obviously talking about any of that stuff today. But you can see here, there's some number of widgets that are available in the store. And if you went and peeked in the database, you would expect to see a table that has products, that has the name of the widget and its inventory, and go figure, those values match. If we go over and look in the Providence table, we can see here that we actually started with 100, and then we saw somebody sold one, and then somebody sold another one, and we decremented that value twice. And so we can see that for each of these individual transaction IDs, when that change was made and when that change was deleted. We use the transaction ID as a logical timestamp, essentially. Now, how does that data get from the app database to the Providence database? As I said earlier, we use WOW record transformation. So as I mentioned earlier, when Stonebreaker originally designed Postgres, he wanted to get away from write-ahead log. And modern Postgres does not embrace that theory, right? Postgres uses a write-ahead log like most of the other major database vendors out there today. This is, as I mentioned, a standard part of what Postgres does. So if you're not familiar with it, the write-ahead log, logical replication, describes every change that's made to your database. Right? The whole idea of this is I'm going to ship these logs from server A to backup server A so that I can, if I have a problem with my primary server, I can switch over to my backup with a minimum of downtime and lost data. Now, we actually use WoW to JSON. Our original prototype of this was built in TypeScript. The current version is built in Go. And this just makes it easier to parse those messages. It doesn't really change anything. It just makes it easier to parse. So, but it also makes it easier to put on a slide. So this is an example of the kind of record you might expect to get out of your write-ahead log. So you can see here we have information about the transaction that's making the change, the table, the kind of change. This is a pure insert, the column names, the column types, the schema information that you need in order to be able to, replicate your information to a separate table, and the column values. So all of the information that you would need in order to be able to build a hot standby of the original server. And we take that and we transform it. Now, this is, again, a very common scenario, right? We see this in analysis databases all the time. This is an ETL type of pipeline: extract, transform, and load. We are applying that. We saw what that data looked like a couple of slides ago. We're making that kind of a transformation on this data, right? And it's important to realize that these Providence records are append only. The only change we ever make to any existing values in the Providence database is to update their information about their deletion. What transaction were they deleted in? And we can also garbage collect, but we'll talk about that in a few slides. So to give an example of what some of these things look like, for like an insert, we're going to set the begin transaction to whatever the current transaction is, and we're going to set the end transaction to infinity, this sentinel value that we use to indicate that it's the current value. So when we originally inserted that there were 100 widgets, that was part of transaction 24818, and it was an insert, so we don't have a end transaction ID. For delete, we go and find the current value that has end transaction of infinity, and we update it to whatever the transaction is that we're currently using. So in this example here, we have deleted that record in 24824. So we're modified. This is the only kind of modification we do in the Providence database. It's slightly more complicated. We'll talk about that when we start talking about time travel debugging, but this is basically the only kind of change we make. And as I mentioned, an update is basically a delete followed by an insert. So here we have, instead of deleting the fact that we had 100 widgets, we're decrementing that value to 99. So we update the original row to indicate that it's been deleted, and we add a new row with the new value and the same transaction ID. And you'll notice that these two transaction IDs match because it was updated in this transaction. Now I mentioned garbage collection. It is possible to do garbage collection with this approach. You can, we still have the same kind of questions around performance when it comes to database bloat. Right? You can keep this data for a very long time if you want. When it comes to storage, the world has changed quite a bit since 1998. We at DBOS will provide you for free a 3-day retention for all of your time travel data. If you are a paying customer, we'll keep it for 30 days. And if you're an enterprise customer, we can basically keep it an arbitrary amount of time. Right? So one of the things that you can do about this is that you can control that retention policy about how long it is that you keep the data. And it's relatively straightforward to go through and delete records based on that same end transaction timestamp information. So if we imagine that here's this same history information and we have this collection of transaction IDs, if we say, gee, we would like to collect up to this point, then we can go and look for all of the records that have an end transaction ID that is less than the value that we are trying to collect. So this is how we go through periodically and clean out, for the accounts that have a time limit on the amount of Providence data we keep, we go through periodically and delete old records based on this information. Now, I mentioned the fact that there's also this idea of the time travel proxy. Now, this is the part that I like to talk about the most, primarily because it's the part that I built. DBOS as a company started as a research project between Stonebreaker's group at MIT and the Advanced Database Research Group at Stanford. And one of our co-founders is a brilliant woman named Chin Lee, and she did all of the research that backs all of this stuff. I built this, but it's entirely her research that drove all of it. And it's been a highlight of my career to get to work on this stuff. But it's also my favorite because it's the part I know intimately and internally because it's the part I built. In my career working in developer tools and developer relations, this idea of natural and familiar has been an extremely big deal to me. I'm a very big believer that developers have their favorite tools, their favorite languages, their favorite platforms, their favorite processes. And if you want your tool or your process or your product to get involved in their process, you have to meet them where they are. You have to make it as similar to something that they're already doing as humanly possible. Right? It's, developers, like everybody, want to be able to get as much stuff done as humanly possible in the least amount of effort. And so the time travel proxy provides that kind of experience on top of the historical data. Right? This data is not the same data in your app database. It has all these extra columns. So how are you going to query it and be able to make any sense of it? You can if you want to. We'll look later when we talk about a demo. You can actually just connect to that Providence database and do whatever you want. Well, you can't write to it, right? We don't give you permission to write to it, and you wouldn't want to, right? Like any analysis database, it doesn't do you any good to write. The time travel, no paradox is allowed. You can't go back and change the data from the past. So you don't want to actually write to it, but you can query it and read it any way you want. But what you really want is to make it read the way that you would query your normal application database. I want to be able to say, select these columns from this table as of this date, not have to come and do a whole bunch of complicated additional stuff. And that's what the time travel proxy does. It implements the Postgres wire protocol. You connect to the proxy the exact same way you would connect to Postgres, whether you're using administrative tools like pSQL, dbeaver, or pgadmin, or you're using it from your application in your code. It just speaks the Postgres wire protocol. It doesn't have any internal data. It sits in front of that Providence database, so it's doing a translation of all the incoming queries, executing them against the Providence database, and then transforming the results back as needed to send them back to you. Well, okay, so it does track one piece of information. For every connection, it knows what you want now to be. That is the only thing that it tracks, right? And as I said earlier, we use that logical transaction ID as the timestamp, as the now. Of course, if you're going to keep track of the current time, you also have to have a way to modify what you mean. Where do you want to time travel to, right? So we actually implement a couple of custom commands, which we'll see in the demo, that allow you to set that time as you see fit. Then, for any queries that come in that are not for these kind of custom commands, we do a set of transformations. Right? Again, as I said earlier, this is similar to what Postgres is doing internally for transaction management with its MVCC protocol or its MVCC implementation. But we're going to talk a little bit about what those transformations all look like. And the idea here is that for any given query, we want to read what the visible versions of the records involved were at the time that the user specified now to be, including now being today, present, whatever that is, the latest information that is in the database. So let's see an example of what that looks like. So we've been using this product table in a couple of other parts of the slide. So we see that we have this history information. Now, when you first connect to the time travel database, it defaults to now. It defaults to the latest information that's in the query, that's in the repository. So if you do execute the query, it's going to say, I'm going to go look for the information where the timestamp for end is infinite. This is this sentinel value. And we'll get back that row. If you then say, I'm going to actually issue a change to the timestamp. I want to change to a different period of time. So all of our custom commands are prefixed with the word DBOS, because that's the name of the company. And, I'm an engineer, I'm not a marketer, but, hey, that seemed like a good way of doing some marketing. Remind you when you're using the product. No. And you'll notice that I actually have the transaction ID in brackets. So we actually have 3 custom commands: DBOS timestamp, DBOS workflow, and DBOS snapshot reset. You do not actually specify the timestamp as a logical transaction ID directly. You either specify a wall clock time or you specify a DBOS workflow identifier. So DBOS, as I mentioned, is a durable execution framework. It lets you run these long-running workflows and automatically recover them in case of a hardware crash, in case of a software fault, in case CrowdStrike pushes out a new update and it screws you over. We use that and map that to a timestamp on your behalf. I'm not going to talk about that whole framework very much, so we're not going to get into the details about how all that works. So that's why I put that in brackets. So you're specifying the logical transaction ID, but you're not doing it directly as it looks like in this command. But now when I execute that command, well, first when I execute the first command, it changes what the connection thinks of as now. So now it's set it to 24825. So between the two values of this change. So when I execute that query, it's going to come back with this row because that's the value, that's the row that has the value where they begin the current transaction ID is between begin and end.
Question.
Yes, please.
When you talk about the begin transaction ID, end transaction ID, there's a possibility that end transaction ID can be less than the begin transaction ID if the transaction wraparound happens. How do you handle that?
So the question was, how do you handle the wraparound? And we're using 64-bit ints for this right now, and I'm not 100% sure I can answer your question right this second. Can we take that to the end? I may have to follow up with you offline on that one. So if we execute another command to say, hey, we want to change the timestamp again. Same kind of thing happens. We move it to another spot. Now we get a different row. And we can also, of course, change this to a timestamp that occurs even further in the past, like before any of this information was inserted, in which case when we execute the query, we get no rows back, because at the time, there were no rows in the table that had that information. So we actually use the built-in features of Postgres in order to be able to determine what rows are or are not visible at any given time. There's an existing command called pg current snapshot that returns a bunch of information about the current transaction status. The minimum transaction that's visible, the maximum transaction that's visible, and a list of other transactions between min and max that may or may not be visible because they're not committed, right? Because of course, you don't commit one transaction at a time. Transaction 1 starts, transaction 2 starts, transaction 3 starts, transaction 2 commits. Now, if you start a new transaction, 1 and 3 are still in flight, even though 2 has committed. So it isn't purely serial like that. So we've been talking about this in terms of these kind of internal concepts of begin and end, but it's actually somewhat more complicated than that. So what we do is we essentially add these query transformations, we add these clauses to each query, right? So we actually parse your SQL command in the proxy, add these clauses to it, and send that along to the Providence database. We recently actually switched. When we originally wrote the proxy, we used the Cockroach DB SQL parser, and we've recently moved over to using the actual native Postgres parser. The PG Analyze folks have built a Go package that wraps that. The reason we used Cockroach originally is all this code is internally written in Go. Anyway, so they wrap the actual PG parser in Go code, which turns out to be fun for cross-compiling relative to doing it in Go, but is actually, it gets you exactly what you want. The cockroach parser is really, really good, but it does a couple of things like, oh, current user. You think that's a variable in Postgres, but in Cockroach, it's a function. So it will silently upgrade that. So if you then you generate an abstract syntax tree from the SQL, you do transformations on it, and then you bring it back out to SQL to send it to the server. It's done things like it's made current user a function instead of a user. So we had to change the actual library that we were using. The first part of this selects all of the versions that are already added by committed transactions, and then we also then filter out the transactions that have not already been deleted. So if we go back and we look at this original query, select select from products where we're at 24825. We transform the query so that it looks basically like this. Now, as I said, there can be more complicated information that's in the transaction snapshot, like the XIP list and stuff like that. But this is essentially the kind of transaction transformation, query transformation that we do. Now, I have to be honest with you, I've been lying this whole time. It's actually more complicated than I've shown you on the slide, right? Because of, as I said, my favorite part, time travel debugging. So it turns out that this approach works really, really well for many, many scenarios, but it does not sufficient for time travel debugging. You need more information for time travel debugging. Because time travels, you have to think about this on a statement by statement level, not a transaction by transaction level. So you can imagine I'm going to make some changes to my database in a transaction. I'm going to update all of the inventory to 50 that start with the word premium, but I'm going to go through and modify premium widget to be inventory 100. I've touched this row twice in this transaction. And that information is not available in the logical replication log, right? So we have to deal with the fact that in code, and certainly within the DBOS framework itself, right? As I mentioned, DBOS is a framework for durable computing. We have long-running workflows. One of the things that those workflows can do is call out to transactions, your code that's reading and writing from your Postgres database. And we expect a lot of times those to be multiple statement types of transactions where you're making multiple changes. We start the transaction on your behalf, you make a series of queries within that transaction, and then we commit it if you don't throw an exception. Otherwise, we roll back. So part of the challenges are I have to be able to read my own writes, right? I have to be able to see the state as it exists currently within the state of the transaction. And it may be that I will write and read and write again. So the value at the end may not be the value that you were seeing in the middle of your transaction. And as I said, WoW doesn't track SQL statements, it tracks transactions. Transactions can be multiple statements, each statement can modify multiple records, each record can be modified multiple times. So in and of itself, we need more than just tracking the begin and end transaction in order to be able to do the kind of time travel debugging that we do with DBOS, and we'll see some of it in a minute. So first off, we transform all of our queries into select queries. I mentioned earlier, you can't really change the past. So if you go and you do an insert, you're not really inserting anything into the Postgres database, right? What we're going to do is we're going to do that insert, we're going to translate it into a select statement to determine how many records you would have actually modified had you executed this command at the time. And of course, a lot of insert and update commands will have a returning clause. So, in those kinds of cases, we do that so that we can actually get the return. So we turn it essentially into a select just the values that would have been returned. And we do this regardless of time travel. We do this for all. It's just a scenario of if you're connecting to your time travel database with something like pSQL, you're probably not trying to do inserts. But if you're trying to debug your code, you're absolutely going to run into scenarios where you're doing inserts. We keep track of which statement within the transaction made which change. So what we basically do is when we start a transaction, we also start a counter. Every query you make is a next, we increment that counter, right? So in addition to being able to track the begin and end transaction, we also track the begin and end sequence, the statement ID for each command. Now, the vast majority of the time, this is very simple, right? The vast majority of SQL transactions are single statement, single query within the transaction, and most of the time, these kind of read your own rights, that's not a particularly common scenario, but it does happen, and we did have to design for it. We then have Postgres triggers to track how many records are changed per statement, and we add that information into the WoW log. So we're adding custom information about your transaction to the WoW log so that we can reconstruct that correctly as part of the WoW exporter. So let's see a quick demo. Let me see how much time I have. Oh, look at that. I've got, 15 minutes. I'm actually ahead of schedule. I may actually lead you guys out early. Okay, so. Yeah.
Not to be in the Providence database, but also in the application database too. Means every application query has to go through this proxy.
It wouldn't make any sense to, the question was, can you connect to the app database via the time travel proxy? I'm just getting it for video. So no, you can't, because first off, it's going to be adding queries for columns that are not there in the application database. So the begin and end transaction, the begin and end sequence, those are tables that are not, they either don't exist or are not visible in the app database. So those queries would not execute correctly. And you obviously don't have all the history information in the app database. So it wouldn't make any sense to put the time travel proxy in front of the app.
Because when you mentioned begin statement and you're making all the changes, insert deprecated. But as you said in the beginning, that Providence database, you don't do any changes, you just only read it.
Yes.
I'm just trying to connect the dots between what is that begin statement where you're converting the update into the select and trying to emit the wall log messages, which usually happens on the source database.
Well, so I'm not, could you repeat the question? I didn't quite follow it.
Right. You mentioned we have a begin and end statement.
Yes.
Within a transaction, if you do a multiple update, wall emits only one changes.
Yes.
So when you pass it to the time travel, it basically takes the update statement, convert that into the select, so that it emits some changes in the wall log so that the target can understand the changes going through. So my question is, all those changes, like changing the update into select, happens to the time travel proxy?
Yes. No, it happens to the time travel. I see what you're asking now. So the question is, are we transforming insert commands into select commands in the application database? No. What we're doing is, if you issue a insert, update, or delete command against the Providence database, which you will do in code, we will actually see it in, as soon as I get to the demo, those commands get converted into select statements. Because the idea there is that even when you do an insert, update, or delete, you're getting data back, right? You'll get back, if you just do a blank insert, update, or delete, you'll get a return value telling you how many records were modified. And in PostgreSQL, you can also add a returning clause. So you can, for example, I'm going to insert into this database. It has a auto increment product primary key, and I want to get that primary key back. And I want to do all of that in one round trip. So insert this information, generate the primary key on the server side, and return the primary key to me as the caller. So those kind of queries, we still need to be able to execute them because that's what lives in your code. Your code has insert commands in it. So we need to be able to transform those insert commands when we are time travel debugging, when we are running against the Providence database. In fact, when we do the time travel, we actually switch which database you're connecting to. So if you write your code and you want to run it in normal debug mode where it's modifying a database, it will connect to your normal Postgres database. If you run under time travel, we connect it to a different database. And that happens for you automatically under the hood. Like we take care of that for you. And so when you connect to the Providence database, that's when we do the insert, update, delete transformation. So that way your code running sees the same result back from the time travel proxy that it would have seen when it was running against in real time against the application database. Does that explain it? Everybody got it? Cool. Okay, so let's see the demo. No, this is great. As I said, I'm running ahead of time, so we can take as many questions as you want. Okay, one more.
Well, you didn't mention anything about indexing. You want to demo?
I'm not going to talk about indexing today. As you can imagine, we do indexing based on the information in the original index, plus we index the begin and end transaction information. As I mentioned at the very beginning, we've been pulling data out of production systems and putting them into analysis systems for a long time. The usage patterns and the execution behavior of that read-only Providence database is radically different from your product database. So the indexes that you want may be different for read-only time travel queries than you do for transactional updates, right? You're talking about the difference between a write-heavy database and a read-heavy database at its very core. And so those indexes are different, and I don't really have time to talk about them, and that's not really the part that I built. So as I mentioned, Qian Li is this brilliant researcher out of Stanford that I get to work with. She's the one who did all of the WoW export stuff, and she's the one who designed even all the parts that I wrote, like all the transformation stuff that we just talked about. She designed all that. So I'm not quite as comfortable talking about how we do the indexing. So let's switch over. I'm going to switch over to duplicate screen so that way you guys can actually see. Oh, look at that. It's actually working. Okay, so this is the DBOS Cloud Console. It's very exciting. And we're going to see the application that we've got up and running to show you that, yes, it really is that you can see here. We saw that screenshot earlier. This is the full screenshot. The whole purpose of this demo is to be able to do things like demonstrate recoverability, which is why you see it's very atypical to have a giant crash the application button in your application, but that's part of the point of this, right? So the real part of the app that a normal user would see is just the center part, and the stuff on the left and right is there for demonstrating some of the other aspects of DBOS that we're not really here to talk about today because we're here to talk about time travel. So if we come over here, we're going to connect to this. Let me just close a couple of these windows down for a second. Yes, I want to terminate this. I'll bring up a new one in a minute. So I actually have 3 Postgres connections here. I don't actually have a local Postgres running right now, but I have my DBOS cloud, right? So when you sign up for DBOS, you get a Postgres server in the cloud, and you'll see here that on this we are running 3 different databases: the widget store, the DBOS Providence database, and then what's called the system database. And so that's part of the actual running implementation. So if we open up here, we can see that we have a DBOS schema. That's for our we use that for, those are our system tables essentially. And we're using connects for migration, so you can see that. But if we look here at products, we can see here, let me just shut this down. We can just do a simple query here. You can see we've added, as I talked about before, begin and end transaction ID and begin and end sequence. And as I mentioned, the vast majority of the time, you're just going to have a sequence of 1. Right? Because most of these SQL commands are going to be really simple. If we were running this against, say, the TPCC benchmark, which we've ported over to DBOS, those would be a lot, more, because those run a lot of multi-statement transactions in a single query, or in a single transaction. Multi-statement transactions, sorry. But as I mentioned, trying to select against this kind of data isn't very useful. Like it's hard to select information against this. So what we're going to do here is we're going to actually go to the Visual Studio Code extension for DBOS, and we're going to launch the debug proxy. And let me see here, where's my terminal view? And so we have this, oh, I guess it was already running. Here, let's shut it down here and start it again so we can see it running from the beginning. So we can see here the time travel proxy running. Now, real quick, I mentioned about the fact that it is, we track the connection, we track time travel state on a per connection basis. This today is deployed on your machine. This is a native executable written in Go. We automatically download it as part of the extension and run it locally on your machine. And then it connects to the Postgres Providence database, which is running in the cloud. It turns out for security purposes, it's a lot easier if you just run it locally and don't listen on anything other than localhost. We could make this multi-user and host it in the cloud, and we may do that at some point in the future, but that's just not how we're doing it today. And so now, if I go back to this database tool, I'm using this built-in to, well, it's not built-in, right? It's an extension for Visual Studio Code. But you can see here that I'm going to do the same kind of thing that I might do with a dbeaver or a pSQL or whatever. And so you can see here that we have this log that's showing us how to connect to all this information. And if I go and I look at the products table here, now remember, I'm still looking at the Providence database. We looked at the Providence database a minute ago and we saw those extra columns, right? Here they are. Now I'm going to close this down and I'm going to bring this open here, and you'll notice that they're gone because we are automatically transforming the query to add the time travel information and then extract that time travel information when necessary. When we return the columns back to the user, we extract that time travel information. We don't send that back to the user. So I can actually interact with this the same way as I would with any other type of system. In fact, let's just go ahead and open up pSQL right here. Now, actually, before we do this, I am going to do one quick thing. I'm going to look at the workflow status table, and I'm going to grab this value, because I'm going to need it. Okay, so now I can close this. So now I'm running in pSQL, and I can say select star from product, probably not capitalized. And we can see here that there are 10 widgets in the database. I realize that this is a trivial database, so please bear with the fact that I have exactly one product in my catalog. We're not Amazon yet. We're working on it. No. So now I'm going to say DBOS. I'm going to spell DBOS correctly. Workflow, and I'm going to give it that workflow. Every workflow in a DBOS application has a unique identifier. And now when I say select star from products, you'll see that I have 12 items in the database. So I get that same kind. I don't have to think about any of this, like how the time travel query information works. I just get to connect to it like I would connect to my application database and explore using select statements. I just also have this extra tool of being able to say, go to this time slot, go to this workflow. And as I mentioned, we use this information, like for example, these are all the workflows that have run in the system. And each one of these, as you'll probably be unsurprised to find out, has a timestamp. Like when it was created, when it was updated, that kind of, oh no, those are application ID. Maybe I'm supposed to look at the transaction state. But the point is we keep track of when each of these starts. So if you say, I want to move to this clock time, we find the transaction, the closest workflow that started at the same time. If you say I want to move to this workflow, we go find that workflow and we find the transaction that's associated with that time. But as I mentioned, I'm here to talk about time travel debugging because that's really my favorite part. So let's open up the code here real quick. This is the payment workflow that occurs when you push the big green button to buy a widget in the application. So this is pretty straightforward kind of stuff. You can imagine, in fact, let's walk through it in code real quick, in the actual application running. I'm going to hit buy now, and it's going to bring me to a payment page. Now in a real app, in fact, the original demo for this app, we went out to Stripe. But setting up Stripe and all that kind of stuff is really complicated, and it was great for us to troubleshoot and for prototyping, but it wasn't something we wanted our users to do. So you would imagine this, do you want to confirm payment or not? That would be on some external site. And we've actually implemented it that way in the code under the hood. And if I say yes, and we can see here that we're at 9 widgets in the store. If I say deny, it goes back to 10. Because the way that the workflow works is subtract it from inventory, then process payment, and if the payment fails, return it to inventory, and if it succeeds, then ship it, right? And we can see here, if I do it again, buy now for 9, we can see here we also have information about the orders that are processing. I hit pending, and it says it's been paid. And then there's a bunch of other sample code here that's going to then dispatch the order, which we're not going to look at. So here it is in code. So you can see here, we're going to start by subtracting inventory. We're going to create an order. We're going to set this event to say that it's complete. That's to be able to talk back to the UI. We're going to wait for the payment to come in. And then if the payment is paid, we mark it as paid. Otherwise, we error out the order and we undo the subtract inventory, right? So this is pretty straightforward stuff. But you'll notice here we have this code lens for time travel debug. So if I click on that, it's going to take a second, and it's going to go up to the database in the cloud and find out all of the runs of this specific workflow that are available. And I can pick any one of them. I'm going to pick the oldest one because that's the one I've rehearsed with. And it will then spin up the debugger. It's going to build the code, and it'll spin up the debugger. It spins up, if it isn't already running, it spins up the debug proxy. The debug proxy does, by the way, send out, like it'll show you like how it modifies query statements and stuff like that. But we're not going to really look too much at that. And so you'll notice here that we've stopped. I've set a breakpoint in the subtract inventory. To be very clear, this is the vanilla TypeScript debugger in Visual Studio Code. We have done no work in the debugger. All we've done is add the code lens that automatically triggers the figure out which workflow you want to use and sets up the connection to the database correctly. And so we can walk through it and we can see that as of this time, we had 1, but what we don't really know is how many were actually in the database. So let's do this. Let's change the code. I told you that I have built time travel debuggers in the past. You don't do this in time travel debugging usually, right? Usually you're capturing a trace of your code, and if you change your code, your trace is worthless. But here, because we're not time traveling the code, we're time traveling the database, we can actually change the code. So now I can go through and make changes to my code so I can find out what the state of the database was at that point in time within the scope of my code. So now I'm going to close this down. I'm going to go back to that operation. I'm going to time travel debug it again. And this time, it's going to rebuild the code. It's got all that stuff up and running, so we're just going to close this down, and it's going to stop there. And now this time, as we go through, we'll see here that we were able to query the database to find out how many items were left in the database after we were done. And even though we saw, right, when we ran it in production, we saw that there were 9 items in the database, here we can see that it's 11, right? Because once we were done, there were 11 left, right? And if I pick a different value from that original time travel drop-down box, as I said, I've rehearsed this way. We pick, say, the second to oldest one. We run that exact same code. It'll rebuild it, but of course it's the same this time. And we step through it again. We'll see this time that there's 10 items in inventory instead of 11. So even though this statement here, right, this is an update command, right? This update command here, as I mentioned, we modify the update command into a select command, so that way when you get this update, you get what you would have gotten back if you were running this in production at normal time. Okay, so that's the demo. And I only have like a couple minutes left, so let's finish this off here. So if you want to try this, we have a tutorial and a case study up on our website. This is for the tutorial, I believe, the QR code. And in summary, DBOS's time travel stores their history information in a separate provenance database to eliminate the performance issues you have with other types of time travel scenarios. We use logical replication into a multi-version format so that we can keep track of all the transaction information that is associated with your data changes. We use a time travel proxy that provides a natural and familiar query experience for the user against the provenance database. And we use intra-transaction statement tracking in order to enable the kind of rich time travel debugging that you only get with DBOS. My name is Harry Pearson. I'm a very big believer that the only way to build good products is to talk to great customers. So that is my contact information. That is my email, and I am available on many social medias at that handle. We, of course, as you are probably radically surprised, we have our own Discord. That's my handle there. If you want to reach out to me, I'm probably going to be in the expo hall for most of the rest of the day, hanging out in the Postgres user group booth. So if you've got any other questions we can't get to right now, please feel free to come find me. Otherwise, thank you guys so much for attending.
Can you go back to the previous slide?
Sure.
URLs?
Yep.
Appreciate it.
Well, I had to scan me on both. Question in the back. How do you handle schema changes? So all the information you need for schema changes are in that WoW record, right? If you're going to build a standby server, you also have to have schema changes in addition to your data changes. So that information is all in the WoW log. I don't really have the time to get into the specifics of how we handle that, but we do handle those kind of schema changes. There's a whole bunch of infrastructure in the WoW exporter for handling schema changes, handling errors, all kinds of that kind of stuff to make it a really robust and powerful solution. It's not open source yet at this time, but we are working on getting that done. There's a bunch of defensive patenting stuff that's happening first. Okay. Well, I'm not sure the transaction ID is the session variable, right? I mean, the information about the current transaction, like I'm simplifying a little bit for slides, but that query is pretty complicated because if we go back to the query that we were looking at, you have to be able to take into account information about things like oh, hey, maybe if I actually have it on the slide that you can see. You have to have information not only about the min and the max, but also the transactions in process list. So this gets a lot more complicated than just, look to see if it's in between the two, right? But for the purposes of like an hour-long talk, that's way too much detail to get into. But I'm more than happy, as I said, I built all that, so I'm more than happy to talk about all that kind of stuff if you want to. I think, Cockroach's implementation, as I understand it, is, again, internal to Cockroach. So we're not pulling that information out. So when you're looking at, using timestamp, as soon as you get off of a single machine, timestamp gets to be really wonky. So, I think using the transactional ID as a logical timestamp makes a lot more sense since we're replicating the data from the source database into the Providence database. But I don't think it makes that much of a difference, right? I mean, you're basically saying as of this time, we're just handling if you say I want this time, we translate that into a transaction ID for you because we're tracking that information anyway for other things.
Yeah, so I get that
Yep.
it's two different tokens.
Yeah, I don't know.
Why it's in two different why a user of the system does it in two different ways. In Cockroach, you actually put it start from table as a system time.
So the reason we have multiple ones in ours is because of the construct of workflow in the DBOS framework being such a strong construct. I didn't really show it here, but let me just real quick, since I've got a couple of minutes here. You'll notice that there's also, here, hold on a second. Let me go back to duplicate. I'm running late, but I don't see the next speaker, so can I continue for a minute? Is that cool? Let's take a second here. We have a Grafana, every one of your DBOS applications has a Grafana workflow, has a Grafana dashboard. This is gonna be really fun because I did not in fact practice this part, so if the demo gods piss on me, it's your fault.
The next session doesn't start for another 7 minutes.
Oh, cool. Well, are you the speaker?
No.
Okay. Oh, you are? Okay, well come up here and I'm gonna do this real quick. You can start getting set up here. I'll be done here in a second. I was just going to show you that you'll notice that we have this workflow ID here. This is I should have from the last hour. Where's just looking for the. You can see this application is designed to be a little bit more complicated than, okay, it doesn't matter. you'll notice here that if I click on this workflow ID, it's going to try and open up Visual Studio Code. So what we're basically doing is you can trigger a time travel debug session from inside of Visual Studio Code by clicking on the code lens, and it will then go up and retrieve the last 10 runs of this specific function. But if you go to your dashboard and like, this is the one that was the problem, I can just click on that workflow ID and it'll automatically launch in Visual Studio. And of course, you also have that information, right? I can also very easily copy and paste this. So if I want to be able to then say DBOS workflow and then move to a specific timestamp, it's really easy to do that. So we provide both because that's the way that our framework works. Cool? Okay, so I'm going to let the next speaker get up here. Thank you guys all for attending. And thank you for letting me run a little long.